Aero elasticity. Aero elasticity, we're talking about deformations due to aerodynamic forces. Static aero elasticity includes only deformations, not vibrations. So inertia is not considered in static aero elasticity. Dynamic aero elasticity, inertia is also involved. And as I mentioned previously, some instability may arise. The most common instability in air elastic is the flutter. I don't know if you know what flutter is. Flutter may occur, for example, in the airplane wing, and it must be avoided because it may be catastrophic. An excellent example of flutter is the Tacoma Bridge. There are some videos in the internet. You can see the Tacoma Bridge oscillating, and it oscillated. It led to a catastrophic failure. The bridge fell down due to excessive flutter, and it's sometimes this event is sometimes referred as resonance, but it's not true. What happened to the Tacoma Bridge was flutter. You can see that the bridge oscillates up and down, and it's also there are lateral oscillations. So it was due to the wind that um, that led to flutter event. And also, when we have inside dynamic aero elasticity, we have also aero servo elasticity. That is aero elasticity plus the control of the aircraft. And the control surfaces are involved here. They may be automatically triggered to improve stability of the aircraft or to avoid instability. And it's quite difficult to it's very there are a lot of details because besides all the characteristics of the structure, the characteristics of the surfaces are also involved, and also the mechanisms of the surfaces are involved. So it's very interesting. However, it's very difficult to work with. Um, concerning concerning loads analysis, the state of art and the challenges of the professionals that work with this in this area. Um, we're always dealing with very modern engineering tools. Loads engineers are always dealing with modern engineering tools. For example, softwares that help us to determine how the structure vibrates. We have finite element softwares, for example, Nestran. Softwares are very modern, are very robust, so they can provide us, we can deal with very refined models. So we have thousands of degrees of freedom in these models, and this allows us to determine loads in a very refined way. This is why our aircrafts are becoming more and are becoming lighter and lighter. Um, we have also materials modeling is becoming better and better. And also we have rigid body dynamic simulations. I'm talking about mechanisms. For example, landing gears of the aircraft, they are mechanisms, and these mechanisms have their characteristics. Damping, for example, may be modeled. Um, So there is a very good software, for example, Atoms. It allows us to model a complete mechanism of the landing gear, so we can assess the loads not only in the landing gear leg, but also where the landing gear attaches to the aircraft structure. So there are very modern engineers that are available for analysis. Of course, I'm talking about maybe CFD, but not CFD is about aerodynamic, but CFD is something that the loads engineer needs, especially for dynamic air elasticity, because there is an aerodynamic model that is that it's put together to a dynamic model. So they work together in order to determine if, for example, flutter will occur or not. Processing and storing data is a great challenge because, as I said, models are becoming more and more refined. Models are large. So the amount of data that is generated is very large. And for example, the time step of the analysis, time step of the simulations, or frequency step of the simulations is small. So we have uh, very, very big arrays, very large matrices of data. And this data must be correctly processed and stored. And also it must be processed very fast. We have fast computers. However, as information, as data is more, we have a lot of data. So some tools that we must use, for example, programming, it's not feasible to calculate loads using a spreadsheet because it would take too long to determine loads. So programming is necessary to process all this data and also storing data. Sometimes it's necessary to have a lot of space in the networks, a lot of space in the computers, because many data are generated, a great volume of data is generated. Something very interesting for the loads engineering, not only loads engineering, but all aeronautical engineering. We may participate in airworthiness requirements updates because, as I've already mentioned, airworthiness requirements must be respected, must be compliant. However, they sometimes are difficult to be understood, and they really are. So sometimes we may ask the agencies further explanations about these airworthiness requirements, and sometimes due to technology updates, some airworthiness requirements become obsolete, and we may warn them. We may say, "Oh, come on, this requirement is obsolete." And sometimes we need a new requirement because we have a new technology. And it's very interesting to make contact with them and say, oh, come on, you may update this requirement. And they are going to make a lot of analysis, study our request, and then airworthiness may evolve due to our request. And um, that equation I showed some minutes ago is a linear equation because we are almost all of the time we are working in the linear regime. Linearities sometimes are not enough to reproduce reality. When we simulate something, we are simulating reality, and some considerations may be made. For example, considering a linear structure. However, sometimes it's not feasible. It's no longer feasible to consider linearities. For example, F is equal to K times X in a spring, sometimes it's not, sometimes it's no longer valid. When we have large displacements, for example, large deformations, linearity effects um, do not work anymore. So, and also when we have new materials, for example, composite materials, I think I think everybody knows that new aircrafts such as Dreamliner, Boeing 787, and Airbus 350, they have composite. Their main structure is made by composite materials, and these composite materials they present non-linear behavior. They present non-linear deformations. So sometimes it's necessary, and it's more and more necessary to consider non-linear effects. And the theory is quite difficult. Sometimes these non-linear effects are not available in the tools we have. So it's necessary to develop new tools. It's necessary to develop the ways to consider these non-linear effects. About the careers and job opportunities for related to aeronautical engineers and specifically for loads area. Aeronautical and aerospace industry, of course, are always looking for, are always searching for loads engineering, because not only aircraft also have structures that are subjected to loads. Sometimes loads are sometimes dynamic loads, and they are always searching for professionals that are familiar to loads analysis, familiar to loads tools. Mechanical industry, because the theory is the same. When I see a structure, an aircraft structure, or a bus structure, or a truck structure, the mathematic is the same, the physics is the same. So mechanical industry that works with structures that are subjected to loads is also searching for engineers that has loads knowledge, loads skills, and so mechanical industry. Also, those companies that produce the softwares I've already mentioned, the computer-aided softwares, they are always looking for professionals to improve their softwares, to update, and to insert, to put more skills. As I've already mentioned, for example, nonlinear effects, some softwares have, some do not have. So these companies are always searching for engineers to contribute to work, improving the softwares, improving this computer aided softwares for loads analysis, for structural analysis. And of course, educational and research institutions. There are a lot of papers related to loads, related to aero elasticity. Industry is always looking for new new things that are being in the educational and research institutions. Some research institutions, some universities work together with industry in order to exchange data, in order to improve the technology as well, and help aircrafts to become lighter, cheaper, and safer. So this is a very interesting area. It's a very rich area. The mathematics that is involved in this area is very elegant. I particularly enjoy this area, and I think it's very challenging. I think it's very interesting to work with this. I'm sure that some of you think like me. And thank you very much for watching my webinar. Thank you very much for watching my presentation.